Hi everyone, welcome back to Made Easy Academia. So please don't forget to like our videos, shares, so that other two can be able to benefit. Now today we are going to talk about elasticity. So mind you, so all those definitions related to that particular topic that we talk about elasticity. If you download our material, you see them, examples, and more explanation on that. So mostly we base on the calculation aspect. So today's topic is based on elasticity. So, if you missed the previous video, we talk about expansivity as well. That say increase in length per unit length and per degree rise in temperature. That one is when the material expand or compress and able to back to its position. That one is under elasticity. But when the material expand and unable to back to its original position, that one is under linear expansivity. And here we have some elastic materials. Elasticity is when an object compressed or stretched and able to back to its original position. We call it elasticity. For example, if you look at this one, the moment I expand it, what did I use to expand it? I apply a force, right? So the moment I release the force, the object will back to its original position. That one is what we call elasticity. So, but here we have materials that cannot undergo that. For example, if I have a calculator like this, can we expand this calculator? You can see this cannot be expanded, isn't it? It cannot be compressed. At the same time, it cannot be stretched. But like this object, when I apply a force there, by expanding it, when I apply a force, I was able to stretch it. Then the moment I release the force, it's able to back to its original position. So all those materials that can be stretched or can be compressed, we call them elastic materials. We call them elastic materials. So all those objects that can be able to stretched or compressed, we call them elastic materials. So if you check the materials, you will see definition of all this. So since mainly we want to base on the calculation aspect, then we have another thing we call. So now the main thing here we'll be talking about here is the force and the extension it causes. You see, this is the object. When I apply a force, it moves from its initial position. So the moment I release the force, it will back to its original position. So meaning the thing that we'll be discussing about here is the force and the extension. So we have another term we call it Hooke's law. Hooke's law is just a Greek scientist. Science, we have many laws in science. We have like Boyle's laws. We have Charles law, Gay-Lussac, but sorry, we don't have a Gauss law, so that's another thing entirely. So then let's just continue about that. We have Hooke's law. Hooke's law is this Hooke is one of the Greek scientists. He's saying that provided the elastic limit of a material is not exceeded, the extension of an elastic material will always directly proportional to the load applied to it. What does that mean here? For example, you look at this object. If I expand, the more the force I apply to it, the more the extension it will cause. So far, it doesn't reach its limit. The moment it reaches its limit, what will happen? Yeah, it can affect the elastic material. So provided that one, the force applying will always directly proportional to the extension it will cause. Meaning, the more the force, the more the extension. You can see when I apply a small force here, I have a small extension, isn't it? So the moment I apply big force, and we have a bigger extension. So meaning the force, there's one thing you have to know in mathematics. We have what we call mathematics relation here. If I said x is directly to y, what I'm trying to say in essence is that the more the x, then the more the y. Or the less the x, then the less the y. But if I said x is inversely to y, what are we trying to say in essence? It means the more the x, then the less the y. Or the less the x, then the higher the y. So that's the difference between directly proportional and at the same time inverse proportion. So here we are talking about directly proportional here. That is, the more the force, the more the extension. This is just a sign of constant. Here we can have this one to be F is equal to K E. So where this K is called constant. So F is force here. The force applied to the object. Then this is extension it causes. So this K, we call it elastic constant. They can call it elastic constant, or they can call it stiffness. It's still the same thing. Stiffness. Science have beautiful terms. So in some cases, if you ask to calculate elastic constant, or you ask to calculate stiffness, they are referring to what? They are referring to K. I hope you are following, right? That's all we need under this Hooke's law. So provided we have the force applied to the object, we always proportional to the extension, meaning the more the force, the more the extension. So now let's just derive the unit for K here. Since you know extension is like a length, so the length is measured in meter. So now let's just show the unit for K. So from here we have that F is equal to KE. So now if I make my K, the force is also measured in Newton. So if I make my K at the subject, so here we can have, if I divide myself by E, divide through by E. So if this cancels this, I can have K is equal to F over E. So now making the unit, putting their unit one after the other, we know force is Newton and extension is meter. So here we can have Newton per meter. So that's the SI unit of what? SI unit of stiffness, which is an elastic constant. So but in some situations, maybe when you are solving the problem and you discover that this your extension is centimeter, if you missed the previous video, I've already shown you how to convert each quantities either from centimeter to meter or from kilometer to meter. So here, mostly questions, if you are given the value of your extensions in centimeter, would you convert it to meter, unless if the result doesn't require that. So now you can say in general, what we have now is F is equal to KE. So where F is the force, K is the stiffness, at the same time E is the extension. So let's see how we are going to make use of this formula to solve some problem. So how are we going to use this formula? So let's see how we are going to apply this formula to solve some problem. What we have is from Hooke's law. From Hooke's law, we have that we have F is equal to KE. So this is what we have from Hooke's law. So let's see some problem. So question 1. So here we have, they said an object weighing is 0.6 Newton is hung on a spiral spring. It's hung on a spiral spring and causes it to extend by 6 centimeter the object is removed and a block of wood replacing it causes the spring to extend by 10 centimeter. They said, what is the weight of the block of the wood? What is the weight of the block of the wood? You see here, so we go with the formula that we have from Hooke's law. I do tell you that the first thing to be considered under the physics is to first write out the given data. So after writing out the given data, then you can be able to solve that particular problem. So let's first write out the given data. They said an object weighing is 0.6 Newton. You know, I do tell you now, but let me tell you something here. When they are mentioning weight here, it simply means the force. You know, we have mentioned that earlier. So when we have a weight is nothing but force. So now here we are given force to be 0.6 Newton. It's hung on the spiral spring and causes to extend by 6 centimeters. So we have extension to be 6 centimeters. You can see from here the value of our extension in centimeter. So since we have the extension in centimeter, we can convert that one to meter. And how many centimeter make 1 meter? Yeah, fine. So we know that 100 centimeter is equivalent to 1 meter. So here I can have this by divided by 100. So if I divide this, I can have extension to be 0.06 meter. So now, even from this first given data, I can easily find my stiffness. You know, when we say stiffness, we are talking about elastic constant. So from the formula we know that F is equal to KE. So if I make my K the subject, divide through by E, divide through by E, which is extension, we can have our K to be F over E. So now, from the data we have, our force given to us is given as a 0.6, and our extension now is a 0.06. So now, if you check that, so we have 0.6 divided by 0.06. If you check that, of course, we are going to have our K to be 10, and we know force is Newton, extension is meter. So meaning our stiffness here is going to be 10 Newton per meter. But that's not where we are going. They didn't go further. They said the object is removed and a block of wood replacing it causes the spring to extend by 10 centimeter. Meaning, if you are given another extension to be 10 centimeters, so even here, I can still convert this one, since the value of this one is centimeter, that is divided by 100. So here we have, if this cancel this, I can have this one to be 0.1 meter. They now say, what is the weight of the block of the wood? Meaning, we are asked to find another force. You know, when they say weight, which is nothing but force. So since I have already got the value of my K, I can just recall that F is equal to K E. So I'm looking for force now. So the K that we have, what is the value of our K? We got the K to be 10 multiplied by our extension, we have it to be 0.1. So if I multiply this, of course, we are going to have 1 Newton. You can see how we do that. Just master the Hooke's law that say that force is equal to Ke, where the K is a stiffness or elastic constant and E is a extension. So let's see another problem. Look at another question. So here's another one. Question 2. They said a load of 5 Newton gives an extension of 0.56 centimeter in a wire which obeys Hooke's law. What is the extension? Caused by a load of 20 Newton? What is the extension caused by a load of 20 Newton? So these are other questions. I can still solve it using the same process, the same method of the way we solved the first one. So the first thing for you to do, firstly put out the given data. That's the first case. They said a load of 5 Newton. Load, weight is still referring to the same thing, which is what? Yeah, the force. So now the given data, we are given force to be 5 Newton gives an extension of 0.56 meter a centimeter. So our extension is 0.56 centimeter, but you can see here too, the value is in centimeter, we can still convert it to meter, so divided by 100. So here we can have 0.0056 meter. So now, from this data first, I can firstly find my K. Since I know that F is equal to KE, so I want to make my K as a since you have given the value of force, at the same time we have extension, so divide both sides by E, divide both sides by E. So if this cancel this out, we have K is equal to F over E. So our force that we have here is 5, and our extension that we have is 0.0056. So if you press your calculator to check the value of that, so now if you check the find the value by 0.0056, what we have there is we have K to be 892.86 Newton per meter. So the question can go further. They said, what is the extension? Meaning we should find the value of our extension now caused by a load of 20 Newton. That is when the force is equal to 20 Newton. Just go to the formula the same way. That's F is equal to KE. So now I'm looking, so the force we have is 20 Newton. That's going to be 20 Newton is equal to, I'm looking for K. Oh, sorry, we have gotten K, that K is 892.86. Then I'm looking for extension, then divide all through by 892.86. 892.86. So if this cancel this out, we have extension to be 20 divided by 892.86. So what we have here is 0.022 meter. So you can see how we normally have. So in some cases, it might relate to length, because length can be gotten from extension. So let's see one example from that area. And see how we are going to approach it. And see how we're going to approach that one. They said a spiral spring is 25 centimeter long, when 5 Newton hangs on it, and 30 centimeter when the weight is 10 Newton. What is the length? What is the length? What is the length if the weight is 2 Newton, assuming Hooke's law is obeyed. So now this is another case. We are asked to find the length here, but it's nothing. You can just do it in another way of, but you can use similar cases. So let's first thing, let the original length of the spiral spring, let the original length of the spiral spring, let's say is L, since I'm going to look for that. You know, length is related to extensions. So now from the first case, they said the spiral spring is 25 centimeter long when F is equal to 5 Newton. So I don't want to convert so that you can understand better. You know, it means when the force is equal to 5 Newton, extension where we have is so meaning when the force is 5 Newton, the extension we have is 25 centimeters. So now I don't want to leave in conversion. I will later convert it. Look at the formula that we know. We know F is equal to KE. So now if I want to put that one in terms of the length, since we length our original length of that extension to be so if I want to do that one, it's going to be the length apply minus original length now. That is that the length apply, sorry about that, the length apply minus original length. So that's why we are going to have the extension here. The length apply minus original length. Since you know here we don't know the original length, right? So now going to the formula. So then if I want to write the extension here, is going to be the first one we are given the value is going to be 25 minus, since we let our original length of the spiral spring to be L, so we are going to have that extension there to be 25 minus L. So going to this formula for the first case, the first condition given, our force is 5, I can have 5 is equal to K. So my extension here is 25 minus L. So now I can call this one as equation 1. So the second one, they said when the weight is 10 Newton, the other one is 30 centimeters. So for the second case, when the force is 10 Newton, now we can have the extension there to be, what we have is 30 centimeter. That means we are going to have 30 minus L. Don't forget the length apply minus original length. And we are letting our original length to be held. So that for the first conditions. For the first case, I have 5 is equal to K bracket of 25 minus L. And for the second case, we have 10 equal to, so if I apply the formula, let me apply the formula first. I know F is equal to KE. So putting the value there, I will have 10 is equal to K bracket over 30 minus L. So this one can be our equation 2. So now from here, I can solve it simultaneously, or if I like, I can just equate the two together. How? From here, I can make my K at the subject. At the same time, from here too, I can also make my K at the subject of the formula. So now from equation 1, what I have is 5 is equal to K bracket over 25 minus L. If I make the K at the subject, divide through by 25 minus L, 25 minus L. So if this cancel this can cancel this as well. That means what I have here is that K is equal to 5 divided by 25 minus L. So I can just say this one is still equation 1, right? Yeah, fine. And from the second one, what we have is 10 is equal to K bracket of 30 minus L. So still the same. I want to make my K at the subject. Divide both sides by 30 minus L. 30 minus L. So, you know, if this cancel this, I will have K to be equal to 10 divided by 30 minus L. So I can call this as my equation 2. You can see that. So the first one we have is K is equal to 5 over 25 minus L. The second one we have is K is equal to 30, 10 over 30 minus, you know, K is K, we can equate 1 and 2 together. Equate 1 and 2 together. That is, the first one is K must be equal to K. So the first one we have here is 5 over 25 minus L. The second one we have is 30 over 30 minus L. So I hope you are getting it right. We just equate the first one and the second one together. So from here, I can cross multiply. If I cross multiply, you know, this multiply this at the same time, this also multiply this. So let me just clean this side. So if I do that, can we just click? Okay, don't worry. So if I do that from the first one, just take this side. Now, what we have, if you cross multiply there, we are going to have 5 bracket of, you see, what we have here is 30 minus L. I can have 5 bracket of 30 minus L is equal to what we have at the other side is a 10 bracket over 25 minus L. So what's going to be the next step is to open the bracket. 5 multiplied by 30, of course, we are going to have 150. So 5 times minus L, and we have 5L. 10 times 25, we are going to have 250. So 10 times minus L, and we have 10L. So the next step here is to collect like time. The one with L to one side, the one without L to the other side. So if I collect the like times here, we are going to have 250, or anyhow you bring it, you can bring this one to this side. I can have minus 5L plus 10L is equal to 250. So this is plus 150. When it comes here, you are going to have minus 150. So minus 5L plus 10L, of course, you are going to have 5L, 250 minus 150, we are going to have 100. So since I'm looking for L, divide 2 by 5, divide 2 by 5, so we have my length to be 100 divided by 5. What are we going to have? Yeah, of course, we are going to have 20. So before we proceed to that, let's see how we let me just quickly explain this. You see, what we have here is 5 from equation 1 and equation 2. We compare them. So when we cross multiply, 5 multiply 30 minus L. At the same time, 10 multiply 25 minus L. So if you open the bracket, we have 5 times 30. That's how we have 150. 5 times L, then we have 5L. 10 times 25, we have 250. 10 times L, then we have minus 10L there. So the next thing is just collection of like times. The one with L to one side, the one without L to the other side. So we have minus 5L here. You can see we have L here. So then plus 10L is equal to 250. This is 150. So when it comes here, it's going to become minus 150. So minus 5L plus 10L. Of course, we are going to have 5L, 250 minus 150, and we have 100. So since I'm looking for L, so I divide all through by 5. So you can see my L now is 20 centimeters. So I can go to any of these cases. I can use either the first case. In the first case, what I have there is 25 minus L for the extension, or I can use the second case. We see that 30 minus anyone you use out of the two, you are going to obtain the same result for stiffness. So if I apply the first one from the first case, we have extension to be 25 minus L, right? So now our length that we have now is this. We have length to be 20 centimeters, so that means I can have extension to be 25 minus the length that we got now is 20. So now here we can have 25 minus 20. Of course, we are going to have 5 centimeters. So now we have gotten our E to be 5. So we can just convert this. If you divide this by 100, here you are going to have 0.05 meter. So I can apply, go back to the first conditions, which says that F is equal to KE. We have 5 is equal to K, extension now is 0.05. So divide all through by 0.05 is 0.05. So we have my K to be equal to. So now if I take that 5 divided by 0.05, I think we are going to have 100. So meaning our K is equal to 100 Newton per meter. So the downside, we should find the length. Given that the force is 2 Newton, the first thing I will do, I will firstly find my extension when the load is 2 Newton from the problem. So if I do that, can we just clean this side? Let me just clean here. So if I do that, from here we know. So from the data, we are given that F is equal to force F is equal to 2 Newton. F is equal to 2 Newton. So that means for me to find the length, because the length related to extensions. So from here, we know that F is equal to KE. So our force we have is 2. And we have gotten our stiffness constant to be 100. Then we have E. So divide all through by 100. We have divided by 100. Then we are going to have extension to be 0.02 meter. You know, from the one we calculated, we discovered that we find out that our original length is our original length that we got earlier. We have original length to be 20 centimeters. So we can convert that one to meter, divide by 100. Then we have this one to be 0.2 meter. So now to find the length as required, so the length now is going to be original length plus extension. So from the data, our original length that we have is 0.2. You know, it's 20 centimeter, but we have convert that one to meter. We have 0.2, then plus the extension that we have, we want it to be 0.02. So by adding this together, we are going to have 0.22 meter. So that's what we have for the new length. So that's all we have for this Hooke's law. So let's move further. Going to your modulus, we talk about the stress, the strain here. So in case if you need the definitions of all those that we mentioned, you can download the materials to see all those terms. Now we have stress, we have strain, and we have Young modulus. Stress, we have stress, strain, and Young modulus. So in some material they use this symbol gamma or to represent for Young modulus. So what do you mean by stress? Strain. So we're talking about stress. Stress is nothing but the ratio of force to area per unit area. To area. So what does that mean here? I can just say mathematically, I can write this as stress is equal to force over area. So in case if you need definition of this, we are going to include it in our material. So you know force is measured in Newton. At the same time, area is measured in a meter square. So now that means for the stress, the unit is a Newton per meter square. But another situation here is that in substitution, maybe you are solving a problem and the area is not given. Maybe we are given, let's say we are given the value of either diameter or radius. You know, in mathematics, this is circle. The line that divides the circle into equal parts is called diameter, and half of a diameter is called radius, right? So now, if you are given, let's say I'm solving a problem, and in that problem, we are given the value of either diameter or the radius. You know, here I can say radius is half of a diameter. So that means, for example, if the diameter is 20 centimeter now, for me to get the radius, I can just find half of 20. So half of 20 is going to be my radius. So half of 20 here, that's going to be 10 centimeter. So now, so to find the area, if the area is not given, you normally apply this formula: A is equal to pi r squared. So now, if you have this one can only be applied, for example, let's say I'm solving a problem and we are given area and we are given radius to be precise. If you are given radius, you can just say area is equal to pi r squared. Substitute the value of your radius. You know, pi is constant, right? So pi is a constant value. Pi is always at 22/7 or 3.142, depending on the problem. Just substitute the values and square the value of your radius. But in case if you are given the diameter, from diameter we can find our radius because we know that radius is half of a diameter. So then for the strain 2 is nothing but extension over length. Extension over length. Here, if you are given value extensions, at the same time you are given length, you can just apply this and find your stress. But let's see a strain rather. Strain, sorry about that. It's strain. So this is stress. So now, if I want to find the unit for this, you know, extension is meter. At the same time, length is also meter. So meter over meter, you know, that's going to be 1. So that means strain does not have a particular unit. It's only stress that have the unit to be Newton per meter square. So now, if you now have Young modulus, for the Young modulus is the ratio of stress to strain. So stress, from here we said the stress is a force divided by area divided by strain that we have here is a extension over length. From here I can apply the law of reciprocal here. I can have force over area multiplied by length over extension. So here F times L, I can have FL over A E. So this is another unit. So that means if you are looking for the Young modulus, assuming if you are getting your stress and you are getting strain, you can apply that, or you can just, if you are given all the data given and you have to find the Young modulus direct, you can just apply this formula, F, which is force times length divided by area times extension. So it depends on the question that we're solving. So if you are given force, length, area, and extension, you can just apply this one. But if the stress and the strain that you given, you can just apply it from here by saying that your modulus is equal to stress over what? Stress over strain. So let's quickly determine the unit for this your modulus here. The force is Newton. So the length too is also meter, as we know, and we know that this area is meter squared. This one is also meter. So if this cancel this, that means here we are going to have Newton per meter square. Even from here, as I said earlier, we know that the stress doesn't have any, the strain does not have any unit because extension is meter. At the same time, the length is also meter. So by the time when the meter cancel meter, then we have no unit for strain. But from here, we said stress is equal to Newton per meter square. So meaning in physics, both stress and your modulus have the same unit. So let's know down the three formula now. You said stress is equal to force over area. That's the first one. Then we use strain to be extension over length. Extension over length. And lastly, we use your modulus to be stress all divided by strain. So those are the three formula that we need here in order for us to find what this guy is not serious. You better go and get money. Yeah, so now let's see one question from here, then we can move further. So the question that we have from here, they said, so question 1, a force of 40 Newton applied at the end of a wire of length 4 meter and diameter is 0.2 meter. If the extension of the wire is 0.24 meter, calculate figure 1, stress on the wire, figure 2, strain on the wire, then you might figure 3, Young modulus. So given that to take pi to be 3.14. So now, the first thing we are going to do here, we firstly pick out the given data. That's the first thing to be considered. So then they said, let's look at the values, given data. They say the force of 40 Newton. So that means you are given force to be 40 Newton. Apply at the end of the wire of length 4 meters. So luckily here you can see the length is in meter. I told you earlier, if you are solving a problem and you see that the length is centimeter, you are going to convert the length to meter. So but here the value of length is in meter, so you don't need to convert that one. So our length is equal to 4 meter and diameter of is 0.2. So our diameter here is given as 0.2 meter. Now, in the formula, if you check the 3, there is nothing like diameter there, but from area, I mentioned that area equal to pi r square. If at the same time, the radius is not given, but we know when we have a circle, the line that divides the circle into equal parts is called diameter, and half of that diameter is called radius. Meaning, through the diameter, we can obtain the value of our radius. So here, if I want to obtain my radius now, I can have radius to be the half of the diameter. When the line divides the circle into equal parts, it's diameter, so half of it is the radius. So here I can have this one to be 1/2. So my diameter now is 0.2. So if I divide this, of course, we are going to have radius to be 0.1 meter. So since we have gotten the value of radius to be 0.1, we can easily find our area. So what we have here is area is equal to pi r square. So the pi we have to use is 3.14. In some problem, they might not specify the values, but if they give you the value, then you have to use the one provided. So that's 3.14 multiplied by. Now, our radius that we have now is 0.1. So that we are going to have 0.1 square. So this means before we multiply this, we should square the value of 0.1. So that is what we have here is let's put it here as 3.14 multiplied by. So our this one is meaning 0.1 multiplied by 0.1. So if you press the calculator for that, so 3.14 multiplied by 0.1 times 0.1. So what we have here is we are going to have 0.0314 meter square. The radius is meter. At the same time, the other one is also meter. So meter times meter, that's how we have meter square for the area. So they now said if the extension of the wire is 0.24, so meaning here I've gotten the area, we know our force as well, and we are given the extension to be 0.24 meter. So the first question I want to say is to find the stress on the wire. So from the formula we have for the stress, if you check, what do we have for the formula for stress here? We said the stress is equal to force over area. So stress is equal to force over area. Now our force that we have here is 40, so I can have 40 Newton divided by, so the area that we got here is we have the value of area to be 0.0314 meters squared. Or after at the end of the day, you can put the unit there anyhow you like it, it's still the same thing. So that means here we have 40 divided by 0.0314. If you do that, we are going to have 1273.89 Newton per meter squared. So we have our stress to be 1273 per meter square rather. Thank you for that. So now, so the next one we have to find the strain. So if I want to find the strain from the formula we have here, we said the strain is equal to extension over length. So if I put that one, that is extension over length. So here, what do we have on the extension? So from here we have our extension to be 0.24 meter. So divided by our length that we have is 4 meter. So you can see meter cancel meter here. That's why we said for the strain doesn't have any, because the unit of extension will cancel the unit of length because they are the same. So 0.24 divided by this, I think we are going to have 0.6. So meaning our strain is equal to 0.6. 0.06 rather, yeah, of course, because here we have 0. So now, the last one we have to find your modulus. So if you like, you can apply the formula we derived earlier, and if you like, you can just apply the normal one by using stress over strain. We derived 2. So luckily here, we have the value of our stress. At the same time, we have the value of our strain. You can just apply this formula by saying your modulus is equal to stress all divided by strain. So from here, what do we have for stress? We have our stress to be 1273.89 Newton per meter squared divided by strain, we have the strain to be 0.06. So by dividing the value of this, you are going to have, if you press your calculator and check that, we have 1273.89 divided by 0.06. If you check that, what we have is what we are going to have is 21231.5 Newton per meter squared. So that's for the, and if you like, you can use the other one that we derive by putting the value of force and extension, then divide by the other value. But here, since we have the value of stress at the same time, since you have the value of strain, then you can just substitute the two values. So that's all about this in this case. So in some situations, here we are given diameter. In some problem, when we're given the value of area direct, which means don't need the value to find anything like radius or related to diameter. Just apply the value given for the area. So the last area we are going to talk about here is work done by elasticity. So in case if you need the definition of that, if you check our materials, you can see definition for that of work done. Work done in elastic materials. Work done. So work done by or in elastic material. Here from the definition itself, if you recall, we said under elasticity itself, we are comparing two things. We are comparing the force at the same time the extension it causes. And I told you, I even give an example that the more the force that we have, the more the extension is going to cause, meaning F is equal to KE. And I will even solve example related to this one. So meaning, I will say this one, it's of two names. You can use either, you can call it either stiffness. So it depends. You have to take note of that. You can call it either stiffness or they can call it elastic constant. So in case if you need derivation of this, if you check the materials, you see I will use one and I will derive the other one. So work done in elastic material is always given as half K E squared. So meaning it's related to the stiffness, which is an elastic constant, at the same time the extension. But in some two cases, there are some cases that in which maybe you have to find the work done and the value of the constant is not given. We have another way of deriving that. From here we know from this particular Hooke's law, we said F is equal to K E. So now if I make my K as a subject, divide through by E, divide through by E. So if this cancels, we have K to be equal to F over E. So now I can substitute the value of K into these equations. If I substitute the value of K to that, that means that we have work done is equal to 1 over 2, which is half. So my K now is F over E. That's F over E. So here we have E squared. E squared is nothing but EE. So here I can have this one to be 1 over 2 F over E. This one means E and E. So here E can cancel E here. So that means we can have work done is equal to 1 over 2 FE. So let's say this one is the first one and this is the second one. So it depends on the values. If you have to find the work done, if you are given force and extension, you apply the second one. If you have to find the work done, if you are given stiffness and extension, you will apply the first one. So let's know that the formula. So the first one we have is we said F is equal to let's say work done is equal to half K E squared, and the second one is work done is equal to half F E. So anyone you want to use in these two formulas, it depends on the data you have from the problem. If you are given stiffness and extensions, you apply the first one. If you are given force and extension, you are going to apply the second one. Let's just see one question from there. Since this one cannot waste any time, let's see one question from there. Then we round up these chapters. So now, they said, from this question, they said, a force of magnitude 500 Newton is applied to the free end of a spiral spring of stiffness 1.0 times 10 to the power of 4 Newton per meter squared, Newton per meter. Calculate the energy stored. Calculate the energy stored in the stretched spring. The stretched spring. So this is another problem. It's simple and straightforward. So since you have us here, so you don't need to perplex. So let's look at the question. They said a force of magnitude 500 Newton. Our force is 500 Newton. Is applied to the free end of a spiral spring of stiffness. We are given that stiffness. Let's just say K is 1.0. I can just say 1000. Just write it this way. Okay, 4 zeros. That is 1000. Calculate the energy stored. So I'm looking for the energy now. We're looking for the energy. So now you see, if you look at the two formulas that we have, the first one is half Ke squared. The second one is half Fe. And if you look at the data, we are given force at the same time we are given stiffness, which is elastic constant. Meaning none of these two equations satisfy the data given. But you can just recall that F is equal to Ke. Remember this, right? From Hooke's law? Yeah, fine. So this one is 500 is equal to K is 10,000. Then E. So I'm looking for E divided through by 10,000. So if this cancels this, then E here can be 0 can cancel 0, 0 cancel 0. This one can just be 0.05. Cool. So 500 divided by 0.05. So now I have all the values now. I can apply equation 1 or I can apply equation 2. Anyone you apply to the two, you are going to get the same result. So we know that work done, which is energy. I can pick any one of the two. Have Fe. So here we have 1 over 2. So the F that we have is 500. That's 500. Our extension that we have is 0.05. So if you do that, it's times 500 divided by 2. I think that one is going to give us 12.5. You know, energy is measured in what? It's measured in joules. So that's what we have for this elasticity. So when the object stretch or compress and able to back to its original positions, that one is what we call elasticity. The other one is expansivity. So when it expands and unable to back to its original position, that one is what we call expansivity. So this is what we have for this elasticity. So we talk about elasticity itself, how to apply Hooke's law. We talk about stress, strain, and Younger modulus. So thanks for watching. Please don't forget to like our videos, share so that other two can be able to benefit from this tutorial. So thanks for watching.